Okay, welcome to Notes at 17a. We're going to be talking about three things that are related to each other. Independence, which I think we've talked about already. Basis, we may have alluded to that. And dimension, which we've kind of alluded to, but we're going to nail it down here. So all these things are in section 3.5 of the textbook. So one of the things that we do, this book doesn't focus so much on this, but one of the things that we are interested in is kind of building vectors from other vectors. And later in the course we'll talk a little bit more about how we do this. And this is a fundamental task in a lot of signal processing and communications and control systems areas. So those are three fundamental areas in ECE. So the basic idea is we'd like to find some prototype set of vectors, m of them, whatever m is, however many of them, so that when we have some given vector space, maybe R5 or even some less obvious vector space, we'd like to find a set of vectors that we can use to build any vector in that space. So this is the way I like to think about it. So you give me some vector v in that space. I can build it from my prototype vectors by just choosing the appropriate coefficients out in front. So again, the symbology here is just a shorthand notation to say a1 times v1 plus a2 times v2 and so on all the way up to a sub m times v sub m. Now you give me some other vector u that's also in the vector space v. I can build that from the same set of prototype vectors with just different amounts, different coefficients out in front. So it's kind of like these are the ingredients that I have in my pantry, and they allow me to cook any possible meal. So what is kind of the a prototype set of ingredients that I would need. So if you're cooking, you can think well, certainly you're going to need milk, sugar, salt, things like that. But the neat thing here is that we can find a set of these vectors so that for a given vector space V, we can build anything from them. So what we want to do is be able to get any vector just by changing the amounts. And so we can't just have this be any old set of vectors. We need some special ones, and they need to satisfy certain conditions. But it's not like there's just one set of them. We'll see that there are many different sets of these that we could pick. And we also want to have it be the smallest number of elements possible. So, we obviously could stock our pantry with cakes and cookies and all the finished products, and then say, I want to make cookies. You go to the pantry, I've got cookies. We don't want to have everything in our pantry. We'd like to just have some small number, the smallest number of things that would allow us to cook anything or bake anything. Same kind of thing. So that leads us to the idea of a span of a set of vectors. So we say that some set v1 to vm spans some vector space v. If it is possible to write each vector v, little v in big V as some linear combination. So clearly we need the span. We need our set of vectors to span our space. But this says nothing about how many are in there, if there's too many in that set. So basically, needing span says that we've got enough vectors in our prototype. So we're not missing anything here. We can build everything, but there might be some redundancy in here. That's what comes up in the next characterization. So here's some examples in R2. Clearly, this one vector doesn't span R2 because the only thing I can build are vectors that lie on this line. Something out here, I can't build it from a linear combination of that one vector. This set definitely spans R2. You give me any vector, I can pick weights for all three of them, but I could also pick weights for just two of them. Any two will also span R2. So you can see that spanning just tells me that I've got enough, but I might end up with too much. So some things that we can see is that for Rn, we're going to need at least n vectors to span, but not just any n vectors, right? So if we go back over here, we've kind of already seen that we need two vectors to span R2, but if I picked another vector, here's another one that lies right on that one, or even in opposite direction. There's two vectors, but they don't span R2. So I need at least n vectors, but not just any n. They need to be linearly independent, as we'll see. We've also defined orthogonal vectors in the past. Some set of notes. So orthogonal just means that they're at right angles to each other. So any set of n mutually orthogonal vectors also spans Cn or Rn. And that leads us to the idea of linear independence. So we're talking about the same set of vectors, v1 through vm, is said to be linearly independent if none of the vectors in it can be written as a linear combination of the others. So notice that span had something to say about the space, and linear independence doesn't say anything about the relationship of these to the space. It just says something about relationship to each other. So if they're linearly independent, I can't write, say, Vm in terms of all the other ones. If I could, then we would say that they're linearly dependent. And if I could write, say, Vm in terms of all the other ones, why do I need Vm? Anything that I would need to build using Vm, I could build using the other ones, because I can just build Vm from the other ones. So in some sense, if a set of vectors is linearly dependent, there's some redundancy in it. There's something in there that I don't really need, and I could remove it. So let's say that we've got V1 through V4. Let's say that I could build V2 from V1 and V3. Well, anything I can build from all of those, I can just build from these three. If I think that I need V2, well, I can, since V2 can be built from V1, V3, and V4, I don't really need V2. So here's some examples. The example on the left, they are linearly independent in R2, and the example on the right, they are linearly dependent or not linearly independent. So, in this case, I can always write this vector in terms of, say, this vector scaled down to that length, this vector scaled down to that length, and then draw the parallelogram, and I've got that. So that's one way to see it. So this is telling us when we have too many vectors to have a unique representation. And so we can have no more than n linearly independent vectors in Rn. And any set of mutually orthogonal vectors is linearly independent because, obviously if they're orthogonal to each other, you can't build one of them from the others. And so if we put these two ideas together, it leads us to the idea of the basis of a vector space. We need both. Span says there's enough to build everything. So that's what makes this support or a basis of the vector space. And linearly independent says there's none in there that I don't need. And so this says that we've kind of got the smallest spanning set that we could possibly find. An orthonormal basis must be a basis, but every one of the vectors in it is orthogonal to all the others, and they're all unit length. So any set of n linearly independent vectors in Cn or Rn is a basis of Cn or Rn respectively. And that leads us to the idea of dimension of a vector space. We'll come back to this idea towards the end, but it's the number of vectors in any basis. So, we've been dealing with vector spaces that consist of, stacks of numbers, but we've already seen that we could have, 3-element vectors, but they are all constrained to within a plane. So we may be talking about a plane within R3. So we can't just count how many elements there are. We need to look to see how many vectors do we need to form a basis for that space. That's the dimension of it. So if we really do have a plane in R3, the dimension of that plane will be 2-dimensional. So we just got here by talking about sets of vectors, and now we'd like to connect this to what we've been talking about with the matrix A. So suppose this set of vectors that we've been talking about, and here we switched to little n, whereas in the previous slides we were talking about capital M, but it's not a big difference. So suppose we've got a set of vectors, and they are the columns of A. So they're independent. We can say that those columns of A are independent if the null space of A is the 0 vector and nothing else. So in that case, we would have the rank of the matrix is equal to n. There are no free variables, and the null space is equal to just the 0 vector. They're dependent if AX equals to 0 for some non-zero x. That's just another way of saying that the null space of A does not just equal the 0 vector. In that case, the rank is going to be less than full, and there will be some free variables. So let's look at a couple examples here. 1, 0, and 0, 1. So those are vectors in R2. What do you think? Dependent, linearly independent? Well, can you build one from the other? I don't think so. You certainly can't build that one by multiplying that one by something. So they are linearly independent. What about 1, 0, and 0, and then 0.000001, however many zeros you want to put there? Now this is a tricky one. Technically, they are linearly independent, but numerically, depending upon the precision of your computer, they may be so close to being linearly dependent, because if we made this equal to 0, then they are certainly linearly dependent. But MATLAB will actually allow you to go out to something like 10 to the minus 14th or 15th, maybe even 16th before it runs into problems. What about 1, 1 and minus 1, minus 1? Dependent, because all I have to do is multiply this one by negative 1 to get that one. Any 3 vectors in R2? Well, this is what we had been talking about on one of our previous slides. They could span. They don't have to span, but they certainly cannot be linearly independent. So the maximum number of vectors that you can have in R2 that are linearly independent is 2. As soon as you add in a third one, you have to have made them dependent. So not a chance that they are linearly independent. Any set of n vectors in Rm must be linearly dependent if n is greater than m. So here's a 5 by 7. We've got 7 columns. Each one has 5 components each. So the columns are living in the space of R5. So then we can say that the rank of A cannot be greater than, less than, equal to, well, that doesn't quite work. Greater than, less than, some number. Well, it cannot be greater than 5. Right? The largest that the rank can be is 5 because we are in R5. So the rank is the number of linearly independent columns, and we've got 7 columns. So you might think that there could be 7 linearly independent columns here, but there cannot be, because we are in R5. So the largest number that they could be and independent is 5. The columns must be, well, dependent, since we have 7 of them, and the rank of A cannot be greater than 5. So any 7 vectors from R5 are dependent. So now let's connect spanning to the matrix A. We've been talking about linearly independent. So linearly independent has to do with the rank of the matrix. The spanning connects it to just exactly what the column space looks like. Oh, and by the way, the rank connects to what the null space, the dimension of the null space looks like. So we have to ask, are the columns independent? Maybe yes, maybe no. We don't really know. But regardless of whether they're independent or not, they still will span some space, but we need to figure out what space do they span. So if we've got some set of vectors, v1 through vd, there's 2 properties that we need to talk about, as we already said, independence and spanning. So 2 vectors can't span all of R3 even if they are independent. 4 vectors can't be independent even if they span R3. So these are just restating some of the things that we've already seen. So here's an example. This is a basis for R3. This is what's known as the, what is it called? I can't think of the word now, but it's the classic basis. 1, 0, 0, 0, 1, 0. Elementary basis. And 0, 0, 1. So can we come up with another basis? Yes, there are infinitely many bases for any given space. So we see we've got 1, 1, 2, 2, 2, 5. Those are linearly independent of each other. I can't make the second one from a multiple of the first one. What do I put in for the third vector to make a basis? First of all, I know that I'm trying to cover R3, so I'm going to need 3 vectors to do that, to span it. And I need to make sure that that last vector is linearly independent. So how about 3, 3, 7? Can I do that? Nah, that doesn't work, because if I just add the first 2 together, I get 3, 3, 7. So this is just the sum of the first 2. What about 3, 4, 7? Let me clear some of the ink off here. Well, to get 3, I would need to just add those 2 together. And to get 7, I add those 2 together. So clearly, to create the top and bottom elements, I just add together. But when I add here together, I get 3, not 4. So the second one is linearly independent, and now I can put that in there to make a basis. So how can we easily check these? Well, put them into a matrix and do elimination on them. Find how many pivots you got. That would be a way to check to see. So you should have 1 pivot for every linearly independent vector in your set. Now, so what we've just seen here is that we've constructed 2 different bases for R3. So a basis is not unique. But every basis for a given space, so this really should say every basis, we should insert here, for a given space has the same number of vectors. And we've already alluded to that number is the dimension of that space. So one thing we just talked about was putting all the vectors in as columns of a matrix. So for it to be a basis of Rn, there has to be n of them with n elements in each one. So that gives us an n by n matrix. And we just said that if we did an elimination on that, we would end up with n pivots if it's a basis. And that's the case we need to see for it to be an invertible matrix. So that's one way you can check if you can invert it. So there's a matrix A that is invertible, and it gives a basis for R3. Here's a matrix that's singular. We can see that it's singular because if we just add these two vectors together, we get the third vector. And that does not give a basis for R3. Here's another example, 2, 4, 3, 6. If we do row reduction on that, we end up with this R matrix, and we can immediately see that the second row is all zeros, so the rank of this will be 1, not invertible, and so the original vectors are not a basis for R2. So the basis for the column space of A, well, we've got 2, 3, 4, 6. Notice that the second column is just a multiple of the first column. So we could just put in here the first column. So that's a one-dimensional space. That's the column space of A. Basis for the column space of R, well, we could pick either one, but we might as well just pick the first one. So that's going to go in there. Now notice that these are not the same space, right? The column space of A actually has a plane that has two, the elements on the plane have two non-zero elements in general, but the column space for R has only one. The first element is non-zero and the second element is always zero. So definitely different spaces. So again, continuing that example, just writing out the answers to that. So they are not the same space. But let's define a new thing called the row space of a matrix. So that's the subspace of Rn spanned by the rows. So here we're talking about a matrix that's M by N. And so the row space of A, if we just transpose the matrix A, the columns of A transpose are the rows of A. So now the column space of A transpose becomes the row space of A. But let's look at our example here. The basis for the row space of A is 2, 4. Basis for the row space of R is 1, 2. But look at those two vectors are actually lying on the same line. So the row space of A and R is the same. Column space is different. Row space the same. So row reduction doesn't change the row space. It changes the column space, but not the row space. Now we've already talked about how the basis is not unique. We can have many different bases. So let's just illustrate that quickly. Here's R2. We can have our elementary basis being right along the axes. So this is 1, 0, and 0, 1. But we can also pick that one and say that one. There's two vectors. So in reality, we can take any two of those four, and they will be a basis. So remember, they just need to span and be linearly independent. So for any given space, there are infinitely many. But the number of vectors in the basis for a given space will always be the same. And that number is what we call the dimension of that space. So here's a matrix A, looking at the column space of that. So let's just see what's happening here. we can see that the first and last columns are the same, so clearly they are dependent on each other. The first two columns are independent of each other, and the third column is just the sum of the first two. So we've got two linearly independent columns of that. And so they will span the column space. In fact, they're a basis for the column space. So that's the basis for the column space. We just find some set of linearly independent columns and they will span the space. We just have to make sure that we don't miss any. And it turns out that we could also just go through and do reduction of this and find the columns of R that hold the pivot values, and then those same indexed columns of A will be the basis. So if you were to do row reduction for this, you would find that the pivots are in column 1 and column 2. What's the dimension of the column space of A? Well, even though it's embedded in R3, it's going to be a two-dimensional space, so it's a plane because there's only two vectors that span it. So again, saying one more time, I think maybe you're getting the idea here that the number of vectors in a basis for the space is the dimension. And we say it again there. So the rank of A comes from some characterization of the matrix as a whole. The number of pivot columns tells us something about the columns of A, and the dimension of column space A is something characterizing a space that has a relationship to that matrix. So we've already stated that the dimension of the column space is equal to the rank of the matrix. What about the dimension of the null space of A? I think we've mentioned this in the past, and we'll explore it even more. It's the number of free variables. So the number of free variables is n minus r, where r is the rank of the matrix. So this was just laying some groundwork for some terms and concepts that we'll be using as we go throughout the rest of the course. We'll see you in the next video.